Hello students, I am Dr. Sayantani Chall. Today I am going to give you a brief discussion on the topic Introduction to Chemical Kinetics. Hello students, I am Dr. Sayantani Chall. Today I will give you a brief discussion on Introduction to Chemical Kinetics. So in the very starting of the topic, we first need to know what the name suggests, what it deals with. It basically deals about the rate at which a chemical process is occurring, and about also it gives the information about the speed of the reaction, about the mechanism of the reaction, how a reaction is going on to produce the final product from the reactant. So the brief outline of this lecture is about the reaction rate, that how can we measure the rates, about the rate laws on which the reaction rate is dependent, how much amount of product is formed from the reactants, etc. The integrated rate laws and the half-life of the reaction, that means the time at which the 50% of the reactant is transferred to the product, and the Arrhenius equation, that means the change, the effect of the temperature on the reaction rate. So what is the meaning of the term reaction rate? See here, there is a picture where in the first bottle at 0 time only red dots are here. The red dots is indicating that only the reactant molecules is presenting is there when we start the reaction. But as the time is going on, we see that some blue dots is appearing there. That means some amount of product is forming there, and as the time is going on, more blue dots is appearing in the last bottle. That means there is more formation of the product molecules and there is less amount of the reactant molecule. So in a very simple state, we can say that the rate of reaction is basically the change of the concentration of the reactant molecule with respect to the time. So if we take a simple example, say the conversion of N-butyl chloride to N-butanol, if we see the data here, see in the very initial state when the reaction is just starting at time 0, the concentration of N-butyl chloride is say 0.1 molar. Now as the time is going on, the concentration of N-butyl chloride is constantly decreasing, and at the end of the reaction it is becoming 0. So if we measure the change of concentration of the N-butyl chloride with respect to time, we can get the rate of the reaction. So the average, so if from this data, if we want to present the average rate of the reaction, so what is the average rate? Then average rate means the change of concentration of the reactant molecule at any given time interval. This set of data is representing the different time intervals. For any time intervals, if we take the change of concentration and also the time gap, and if we present then this as a change of concentration with respect to the time, then we can get the rate of the reaction. So if we plot the concentration change, of the reactant molecule versus the time, we can get there is a steady decrease of concentration, and the differential format of the rate of a reaction is therefore is represented as dA by dt, where this term is indicating the concentration of the reactant molecule. Also in other term, we can represent the rate of a reaction in terms of the product concentration. So as the reaction is going on, there is a decrease of concentration of the reactant molecule, as well as there is an increase of concentration of the product molecule. So the rate of any reaction can also be represented as the change of concentration, the decreasing concentration of the reactant molecule or increasing concentration of the product molecule. So the negative sign here is indicating that since the rate of the reaction is continuously, the concentration of the reactant molecule is continuously decreasing, so here is a negative sign when we are representing the rate of the reaction with respect to the reactant molecule, whereas the concentration of the product molecule is continuously increasing, so there will be positive sign. But in all these cases, there is a stoichiometry of the reactant is 1:1. But if the stoichiometry is not 1:1, then how to represent the rate of the reaction? Say the very common reaction of the formation of HI from H2 and I2. Now 1 moles of H2 and 1 moles of iodine combine to give 2 moles of HI. For this type of reaction, how to represent the rate of the reaction? So very simply, rate, if we want to represent the rate of the reaction with respect to the hydrogen gas, then it will be minus of del H2 by del T. Why there is a minus sign? Since H2 is the reactant molecule here, so its concentration is continuously decreasing, so there will be a negative sign. But when we will have to represent the rate of the reaction with respect to the product molecule, then we have to divide this rate expression with respect to the stoichiometry of the reaction. So for any general reaction of the type AA plus BB will convert into CC plus DD, then the rate of the reaction can be given by minus 1 by A del A by del T, or minus 1 by B del B by del T, or 1 by C del C by del T, or 1 by B del D by del T. The minus sign, again I am repeating that the minus sign indicating that the concentration of the reactant molecule is constantly decreasing, and the positive sign with respect to the product is indicating that the product concentration is constantly increasing. Now, so far we learned that how to write the rate expression for any kind of reaction, even it is 1:1 stoichiometry or something else. Now, what is the relation between the concentration and the rate law? Again, take an example of reaction between the ammonium ion and nitrate ion giving rise to nitrogen gas and water. So, if we study this reaction with different concentration variations of the initial two reactant, there is two reactant, one is ammonium ion, one is nitrate ion. So, if we change the concentration of the ammonium ion in two consecutive experiments, in experiment number 1 and 2, if we see that the initial concentration of ammonium ion is just double, but the concentration of the nitrate ion is keep constant here, and see there is a double increment of the rate of the reaction. Whereas if we talk about, if we again change the concentration of the nitrate ion in the experiment number 5 and 6, where the ammonium ion concentration is remain same, whereas the nitrate ion concentration is doubled, then again also there is a double increment of the rate of the reaction. So the observation proposed that for this particular reaction, rate is proportional to the ammonium ion concentration, rate is proportional to nitrate ion concentration. Now if we combine these two relations, then it will finally give the final rate expression of this reaction, that means rate equal to K into concentration of the ammonium ion into concentration of the nitrate ion, where this K is the rate constant of that particular reaction. Now this rate constant is very specific for every specific reaction, and it depends on temperature. And again, for the solution phase reaction, we have to represent the rate law or the rate equation in terms of the concentration of the reactants. But if the reaction is a gas phase reaction, then the concentration term is replaced by the partial pressure of the reactant molecules. So from this rate expression, we can see that the power of the individual concentration term is 1 here. So the summation of the power term of the rate equation of the concentration term in the rate equation is called the order of the reaction. That means we can define the order of the reaction as the summation of the power term of the concentration term in the rate law equation. So in this equation, we can say that the previous reaction, that means this reaction, we can say that by studying their relationship, the relationship of the rate for this particular reaction, we can say that the reaction is first order with respect to ammonium ion concentration, the reaction is first order also with respect to the nitrogen ion concentration, and as a whole the reaction is second order with respect to both the reactants. So this reaction is an example of the second order reaction. So we can get first order reaction, we can get second order reaction, third order reaction, etc. But the example of third order reaction is very few. However, so up to now we know that what is the rate of reaction, how to represent the rate of the reaction, what is the relationship between the concentration and the different between the rate and the concentration of the reactant molecule, and what is the standard representation of a rate equation, and what is the order of the reaction. So now finally we have to derive rate equations or rate laws for different type of reaction. So let's first take first order reaction. So first order reaction means simply take the reactant molecule A which is converted to the product molecule B. So rate of the reaction can be written as the rate constant K into concentration of the reactant molecule whose power is 1. So the differential rate expression is therefore minus dA by dt equal to K into A. Now simply by integrating this equation we can arrive at this expression that AT will be equal to A0 into the power minus K into T, where AT is the concentration of the reactant molecule A and A0 is the initial concentration and K is rate constant and T is time. So again this standard equation of first order reaction can also be rearranged by taking ln in both sides in this format. Ln AT by A0 will be equal to minus of K into T. Again A0 is the initial concentration when T equal to 0 and AT is the concentration of A at any time T. Therefore, if we rearrange this first order equation by splitting this ln term as ln AT minus ln A0 equal to minus KT, we can simply compare this equation by the standard state line equation y equal to x plus b. So if we have to plot different concentration term with respect to time for first order reaction, we can get different equation pattern. Say if we simply plot the concentration versus time plot according to this equation. According to this equation, if we plot AT versus T, then the graph will show an exponential line. Whereas if we plot ln A versus T, then this will give a straight line, a decreasing straight line with the negative slope of minus K. So for any unknown reaction, how can we know that the reaction will follow the first order reaction, the reaction will follow the second order reaction, which path it follows for any unknown reaction? Say here methyl isonitrile is converting to methyl cyanide, but we don't know what path it will follow. So the very simple way to go to the experimental process. Through experiment, first we have to collect different data, different concentration of this methyl isonitrile at different time interval, and then if we plot the concentration of methyl isonitrile with respect to time, and if it gives such exponential decay, then or if we plot the ln of concentration of methyl isonitrile versus time, it is give such a straight line, then we can say that the reaction is following the first order rate equation, because both the observation is according to the standard first law rate equation. And also from this experimental data we can also say that this concentration of AT will only 0 at t equal to infinity. If t equal to infinity, then only AT can be equal to 0. At t equal to infinity, this AT can be equal to 0. That means the first order reaction is a never ending reaction. So in this way, if we, for any unknown reaction, if we study the experimental data, if we plot the experimental data, the concentration of the reactants molecule with respect to the time, and if it follows the standard rate equation, from that we can give the conclusion that okay, this reaction is following the first order reaction or second order reaction or whatever. So then if we discuss, now we will discuss the second order rate law equation. In the second order rate law, first thing we have to clarify here that I have written here that A plus A is converting to P. That means both the reactants, we assuming here that both of the reactants is starting with the same initial concentration. but it also possible that both of the reactants may not have the same initial concentration. Let here we assume that both the reactants have the same initial concentration. Therefore, according to our previous knowledge, we already learned how to write the rate expression. Therefore, minus d by dt is equal to k into a square. And if we again integrate this differential equation, then we can get that 1 by at equal to kt plus 1 by a0. And obviously again this followed y equal to mx plus b format. So again if we plot 1 by a versus t, this will give a straight line in comparison to the first order reaction. Here the slope of the reaction will be k, and this is positive, whereas in the first order reaction when we plot this ln at versus t, then we got their negative slope. So now half-life. So what is half-life? Half-life means the time required for 50% conversion of the reactant molecule to the product. So if for that conversion of methyl isocyanate to methyl nitrile, so what happened there? What will be the 50% conversion time, or what will be the T-half? T-half means in this decay curve, the time where the 50% of the reactant molecule is converting to the product molecule. Therefore, at T-half we can see that the concentration of At will be equal to 0.5 into A0, where A0 is the initial concentration of the reactant molecule. So in the first order reaction, if we put this will be this not be second order. So in the first order reaction, if we put here in case of At, if we place the values 0.5 into A0 divided by A0, it becomes to minus k into T-half, then we can get the final expression, that means 0.693 by k will be equal to T-half. So this is the expression of T-half for the first order rate equation, and it is also clear from here that for the first order reaction, the half-life of the reaction is independent of the concentration of the reactant molecule. And for the second order rate law, again from in the second order rate equation, if we put the values of At in place of the At, then we can get another expression, that means 1 by k into A0 will be equal to T-half, and it is dependent on the concentration of the initial reactant molecule. So from this T-half expression we can get, or we can calculate the time required for the 50% conversion of the reactant molecule to the final product molecule. So so far we learned what is the reaction rate, how to write that expression, what is the rate law, first order reaction, second order reaction, etc. So now what is the relationship between the temperature and rate? It's very easy to understand that as we increase the temperature, the rate of the reaction is generally increases, because K, the rate constant, is highly dependent on temperature. So what are the different factors that is affecting the rate of the reaction? Whenever the reaction is occurring, when two or many more reactant molecule is coming close to each other to have a reaction, then what is happening there? First of all, there is a collision between the different reaction molecules. So the factors is frequency of collision between the reactant molecules, the fraction of the collisions which is enough to give the energy to the molecules to give the final reaction product, the orientation of the different molecules. These are different type of factors, along with the temperature, which is important to increase the energy of the reaction to give the final product from the reactant molecules. So first Arrhenius around 1889 give or proposed an equation which is called Arrhenius equation, and the equation is of the format k equal to a into to the power minus a by rt. Through this equation, Arrhenius wanted to propose the relationship between the rate constant k and temperature. Rate constant k and temperature. The concept is like that. Say if we have to pass a ball over a hill, so if we don't give the ball enough kinetic energy, it can't pass the hill. Similarly, for the reactant molecules also, if we don't give the reactant molecules sufficient energy to cross the energy barrier. Every reaction needs some amount of energy, some specific amount of energy, which is called the activation energy for that particular reaction. So reactant molecules must have to be provided that particular amount of energy, that is called the activation energy. After that, the molecule will be converted to the final result. So how the molecule is acquiring that activation energy? Through the collision. One of the mechanism is telling that through the collision between the different reactant molecules, they are acquiring the required energy, the activation energy, to cross the energy hill for a particular reaction and giving rise to the final product. So in this equation, A is called the frequency factor. This factor is depending on the collision frequency of the different reactant molecules, and also this factor A is dependent on the orientation of the different molecules. So again, if we coming back to a previous example of CH3NC, when it converted to CH3CN, this isonitrile is converted, isocyanide is converted to cyanide. What is happening there? Say this is the ground state energy of the molecule. So when the molecule is acquiring some particular amount of energy, that is the activation energy, this is the high energy state, and here a complex is formed which is called activated complex. So the reacting molecule must have to pass through these high energy state where there is a formation of activated complex. This activated complex is very unstable, and then it converted to the final product molecule. So this is the energy of the reactant molecule, this is the energy state of the product molecule, and the amount of energy between this level is called the activation energy for this particular reaction. Now see here that there is a difference between the energy of the reactant molecule and the product molecule. If we go through this graph, then this will be more clear for all of you, that this is the energy state of the reactant molecule, this is the energy state of the product molecule. So there is a gap of energy between the reactant state and the product state. So this amount of energy is released after the reaction, and such type of reaction is called the exothermic reaction. Whereas if we see that the energy of the product molecule is high compared to the reactant molecule, then the reaction process will absorb some amount of energy, and then those reactions is called the endothermic reaction. So the Arrhenius equation is explaining us about the concept of exothermic reaction and endothermic reaction. So this gap is called the activation energy, and here we often use the term reaction coordinates. In the x-axis we often use the term reaction coordinates. So what does that term mean? The reaction coordinate means whenever a reactant molecule is converting to the product molecule, there is a numerous chains, and the most prominent is that old bond is broken and a new bond is formed there. So how this old bond is broken? Molecule is always vibrating, so bond is always vibrating there. Now among the different types of vibrational modes of a particular molecule, maybe one of these vibrational modes is very weak, and those weak vibrational modes is responsible for the formation of this activated complex, break of a bond, old bond, and formation of the new bond. In this way, the reactant molecules, this is the easy picture to understand that how the reactant molecule is converting to the final product molecule. So if we are talking about the temperature relationship with the activation energy, the blue curve is the plot of Arrhenius diagram at low temperature, whereas at high temperature we can see that the peak height is decreasing as we go from low temperature to high temperature. This means the activation energy is getting little bit lower when we increase the temperature, but the number of molecule or percentage of molecule having this activation energy, having this higher activation energy is becoming more and more. Therefore, as we increase the temperature, there is a more increment of collision, and therefore there is a decrease of activation energy Therefore, the reaction is getting more fast. Now, we can calculate this value of activation energy by simply plotting the Arrhenius equation. If we take ln in both sides, therefore if we plot ln k versus 1 by t, we can get such a graph from where we can easily get an idea, or we can calculate the activation energy for any particular reaction. Again, for a reaction at different temperature, we can find out the values of rate constant at different two different temperature to find out the effect of temperature on the rate of the reaction. We already discussed the exothermic reaction and endothermic reaction, and there is therefore there is two pathway to increase the rate of the reaction. One is to raise the temperature of the reaction, and another is to use the catalyst to lower the activation energy of the reaction. So what catalyst does here? Catalyst do not interfere into the thermodynamics of the reaction. It do not disturb the equilibrium state of the reaction, but it simply reduce the activation energy of the reaction. Very simply, if we follow these potential energy diagram for a reaction, we can see here that this black solid line graph is indicating the uncatalyzed reaction, whereas the dotted line is indicating this is the catalyzed reaction, where there is a sharp decrease of the activation energy from the uncatalyzed reaction. Therefore, this is a separate branch where we can discuss in details about how this catalyst lowering the activation energy. However, this use of catalyst to lowering the activation energy to increase the rate of the reaction is very much important part of engineering chemistry for the industrial applications. So up to this this lecture, up to this end, we can say that why we need to study this chapter, this chemical kinetics, this rate law, this activation energy, etc., because all these ideas, all these understandings is important for understanding different chemical process that is occurring surrounding us in the environment, to understand the decomposition of different medicinal compounds, to understand the reaction mechanisms, how the reaction is going on, and also to manipulate or to control the different type of industrial reactions, etc. Thank you.